we derived the expression assuming a variation of voltage in the channel from left to right in a linear fashion. Okay, so if I just show you the voltage variation, what we assumed is that the voltage increases from left to right like this. So this was our channel potential. It was 0 on the source, so this is our source side, and in the drain side, that is when x is equal to L, we have a VDS. So this was VDS. So that's what we assumed. So the entire voltage is dropped across the channel. The applied voltage VDS is dropped across the channel, which is true especially when the device is operating in the, or device is yet to reach the saturation mode. Okay, so let me tell you why. So again, I'm drawing the schematic structure. So we have oxide, on the top of that we have metal, this is our gate, and so we have a depletion region, and most of that depletion region will be extending. So this is the way depletion region will be there for low gate voltage. But then what happens is that as you increase the gate voltage, so I have not supplied any VDS, so if I supply VDS also, so this is my VDS. Okay, so this applied voltage, I said, will be dropped across the channel. So channel will initially come as you increase the VGS value. So this is our VGS. So if VGS is sufficiently high, that is above the threshold, you will have channel here, and then when you apply VDS, the voltage will be dropped across the channel, because the channel can be treated like a resistor. Okay, so if you apply a voltage across the resistor, it will be linearly dropped as shown here from source to drain. Now because the right side is more positive, and you have a bulk region, so we are assuming the case where we are grounding the bulk region, and this is the ground point. Source is always grounded, and this is drain, this is gate, and this is bulk. Okay, so the source is grounded, and we are assuming that the bulk is also grounded, that connected source and bulk are connected together, and that is always done. Or other way you can do is make the bulk more negative. That case we will see what will be the difference in a short while. So if they are both same potential, then you will have a depletion region, because there is a PN junction here, so there is going to be a depletion region here. Similarly, there is going to be a depletion region on the other side, but here the reverse bias, it is basically reverse bias, because VDS is the voltage on the drain and bulk is grounded. So you have large voltage on the N plus on the drain side compared to the P side. So the depletion region width on this side is going to be larger compared to the depletion region width on the left side. Now as you increase your VDS, what is going to happen is that this depletion region width will increase more and more. So in order to show that, okay, let me redraw this. So the depletion region will increase like this. Okay, it will extend more and more like this. So that is because of the rising of the potential on the drain side relative to the source side, and the PN junction has more voltage across it, means we know that the depletion region will extend further into the low doped region. Here the low doped region is basically the P region. The substrate is relatively low doping concentration, P substrate. Okay, whereas N plus region is heavily doped, so the extent to which the depletion region go into the N plus region is very minimal. if suppose 100 times is the doping concentration in the N plus region, that's why we call it as N plus also. So it will not extend much into the N plus region, but most of it will be extended into the P region. Okay, so another thing is that as you now increase this potential VDS, so then you will reach a situation where on the drain side underneath the oxide, the VDS value, that means the potential in the right side of the channel, is going to become at some value of VDS. So let me write it here. As VDS is increased, on the drain side of the channel, the potential will go above, VGS, or let's say VGS minus VT. It will go above VGS minus VT. So if the channel potential is above VGS minus VT, then there cannot be any channel existing there. So earlier the channel was existing from source to drain, because everywhere in the channel we assumed that the potential is lesser than VGS minus VT. So that means the channel can exist. So whenever the gate potential is more than the channel potential by an amount VTH, the inversion layer will exist there. But suppose VDS is large enough so that on the right side we have a potential, so this voltage on the right side become VDS, and if the VDS value is if this is greater than VGS minus VT, then the condition for channel to exist in that region will be violated. So then what happens is that the channel will look in a different way. It will look like this. Okay, so the channel will have more carriers on the left side and it reduces. So this is the way the channel will vary. Okay, so the amount of the electrons there depends upon the potential in the, it will depend upon the potential inside the channel region. So if the potential is more, then the chance for inversion will be less. Okay, whereas in the source side the potential is 0, so entire VGS that is applied will be coming across the gate and channel. Whereas on the drain side, because of this increase in potential on the drain side due to the VDS applied, so on that side you will have a lesser voltage across the oxide layer. Okay, so on the gate side we have VG, on the drain side we have VDS, right? So the voltage across the oxide is going to be VGS minus VDS. Okay, so if VGS minus VDS is not greater than VTH, channel cannot exist. So as you increase the VDS, this will become more and more prominent. So if you consider another case, what will happen? If you increase more and more, then the channel will cease to exist even before. So it will be like this. The channel will be like this. Okay, so it will cease to exist from this point onwards. So channel will be only from here to here, but it won't be present from here to here. Only depletion region will be present there. So this is what we mean by pinch off. The channel is not reaching to the drain side. Okay, so as I have written here, as VDS is increased on the drain side of the channel, the potential will go above VGS minus VTH, or in other words, on the gate side we have VGS and on the channel side we will have VDS, and the difference is not greater than VTH, and therefore will go above, and as a result as a result, the inversion layer cannot exist on the drain side. This result in channel pinch off. Result in channel pinch off and current. This result in channel pinch off and current saturation. So this is the physical mechanism for current saturation. Why the current is going to saturate? The physical argument is this: as long as VDS is smaller, then even if the voltage is dropped across the channel, every point on the channel, the potential is lesser than VGS minus VTH, and therefore the channel will exist from left to right entirely, and the potential that is applied VDS will be dropped across the channel. But as you increase the VDS, we will reach at a point where the voltage on the right side of the channel is going to be greater than VGS minus VTH. Okay, therefore the channel cannot exist in those regions where the condition is violated, and this result in channel pinch off. And once the channel is pinched off, that means there is no way channel exists for some region here, and it is only a depletion region. And how does the current flow? The current will flow. So let me write that also. The current will continue to flow. By a mechanism similar to that of a reverse biased collector base junction in a BJT. Okay, so if a BJT which is biased in forward active region, current flows across the reverse biased region. Okay, there is a collector base junction which is reverse biased, and current still flows through that, because whatever electrons which are reaching there into that depletion region will be swept away by the field inside the region. So there will be electric field in the region, though the electrons are not there, but that electric field will swept away the electrons which reach to the edge of this depletion region. Okay, so the current mechanism is similar to that of a BJT in the collector base junction. How, even though it is a reverse biased region, ordinary diode, when you reverse bias, current doesn't flow, but in a BJT, in the collector base junction which is reverse bias, current flows through it, because a lot of carriers are reaching from the base, which will be swept away by the electric field present in the region. Same is the mechanism here. So there is carriers which are reaching to the edge of the depletion region, and inside the depletion region there is going to be electric field which will sweep these electrons to the other side and resulting in the current flow. So but the current cannot increase right now, okay, compared to the earlier case where the VDS was small, we had a linear operation. That means the current increased with in proportion to the VDS voltage applied. That is like a resistor. Okay, when you apply larger voltage, you have larger current, but that will not happen because the whatever extra voltage that you are continuing to apply, mostly that is going to be dropped across the depletion region, not in the collector, not in the channel where the inversion layer. Okay, so only if the voltage is dropped more and more in the inversion layer, only then the current can be increased. Okay. Okay, but there are some second order effect that we will come into a little later. So let me rewrite the expression that we have derived. So we have derived the expression IDS, that is drain to source current. This current is going to flow in a direction which is in minus x direction. That's why when we derived earlier, so this is the actual direction of the current IDS. Okay, it is going into this direction, which is basically in the direction of x. It is like opposite. So when we derived, we got a minus sign because of that. It only means that the direction of the current is in minus x direction. Okay, but let us take the magnitude of that current, knowing that its direction is from right to left, because electrons are going to go from left to right. So current is going to magnitude or polarity is going to be from right to left. So what is the expression that we got? So the expression that we got was, we did not assume any pinch off there while deriving the expression, because if pinch off is taken into account, this potential variation is not true. Okay, if pinch off is assumed, then our potential will be something like this, or that may be too much exaggerated. Okay, something like this. So the entire voltage will be dropped in a smaller length. Okay, so we have not considered that into account, but we considered that entire applied voltage VDS is dropped from left entire across the channel, that is from 0 to L. So that is a case before pinching off. After pinch off, the entire voltage will not be dropped like that. Okay, so IDS we got it as mu. Okay, what was the expression? Mu n C ox. Okay, so this mu n means mobility of electrons, C ox means the capacitance, oxide capacitance per unit area, and then W by L that we got, and then we had VDS. Okay, so let me write the way we have derived it. We had two terms. One was like VGS minus VTH into VDS, and the other was VDS square by 2. Okay, this is what we got in the last class. So here, while deriving this expression, we assumed that our VDS was less than, its magnitude is less than VGS minus VTH. Okay, this is the assumption under which we have derived. Only when this is true, this is true, only then we can say that the potential is dropped linearly across the channel, because the channel is existing basically from 0 to L. Otherwise the channel does not exist from 0 to L. Okay. So entire applied voltage VDS is now dropped. So that is what this means. Okay. Now, so as I tell, if we try to plot this, okay, that is what we were trying to do at the last part of the class. If we just plot this equation, so this is VDS and this is my IDS. Okay, so very small values of VDS. So this is VDS, and here also VDS square is there. Very small values of VDS. We can neglect VDS square. Okay, like this term will be dominant, and therefore we will. I said that we will have a straight line, and then after some time this will begin to play a role. So this is trying to basically increase. This is always like a straight line. It's like y is equal to mx form. So it's like a straight line passing through the origin. But then because this will dominate and this is having a negative sign, it cannot go like this straight line. It will go now. It will deviate from the straight line and bend around like this. Okay, and this bending will continue. because this will become more and more dominant and more and more dominant. So the increase by this will be compensated by the decrease of this, and at some point it will reach its maximum, and then if you continue, what will happen is that it will bend like this, because this is going to become dominant at larger values of VDS, and then we will have this will go down, like at some point of time it will reach 0 also. So it's like equation of a parabola. But then this is unpractical, that we will have a reduced current. Current cannot reduce even if it pinches off. The channel is pinched off, but the current cannot reduce. Okay, so that is why this is true only when under the assumption VDS is less than VGS. Now maybe it is valid till at this point where it reaches the peak current. So in order to find the peak, what we can do is DIDS. So to find the peak current, find the peak, that is the current just at before the pinch off or just at pinch. To find the peak current, what we can do, so this is like a maxima of a function, so we just take a derivative and equate that to 0. So that means mu n C ox W by L, and then the first term is derivative, if you take it is VGS minus VTH, right, that's all, and the second term, if you take the derivative, you will have half or 2 will come out, 2 VDS, so that will cancel with other 2 and then VDS. So this will be equal to 0. So which means that so therefore we have, so these are constants, so they cannot be 0. So the other term which is in the bracket has to be 0, which means that VDS should be equal to VGS minus VTH. Okay, so this is the condition for pinch off. So we derive the condition for pinch off. Pinch off means the point at which the current cannot further increase. So this is the maximum current that we are going to reach, and once we reach this, we can back substitute this current. So from here onwards, actually this current will stay constant. Okay, so this is basically the pinch off point. Okay, so VDS value at which, so this is basically, this is equal to VGS minus VTH. So depending upon VGS value, that minus VTH, when it reaches, the channel is pinched off and the current is such. So we have the saturation region here. Okay, so up to here it is linear. Then we have quadratic. Okay, so linear, quadratic, saturation. So 3 region of operation. So we can talk about. So the saturation current, therefore, so saturation current is basically the peak current itself. And how do you find the peak current? You just substitute this VDS back into the previous equation. So IDS is equal to mu n C ox W by L, and then in bracket we had VGS minus VTH into VDS. So VDS I am substituting as VGS minus VTH, so it will be square minus then we had VDS square by 2, so which will be VGS minus VTH square by 2. So this is our expression, which you can see that this is like s square minus s square by 2, so it can be written as s square by 2. So this is going to be mu n C ox by 2 into W by L into VGS minus VTH the whole square. Okay, so this is what we will get. So mu n C, so this is going to be the saturation current, or you can call it as ID sat. Okay, that is commonly the way. So this is true when your VDS is greater than VGS minus VTH. okay, under that assumption. So combining the different regions of operation, we can now combine the current expression and write a single equation. So IDS is equal to, so it is going to be 0 when VGS is less than VTH, okay, and then it is equal to mu n C ox W by L VDS into VGS minus VTH then minus VDS by 2. I have taken one VDS outside, and so this is true before the saturation region, that is VDS less than VGS minus VTH, and we have also mu n C ox by 2 W by L then VGS minus VTH whole square. So this is basically the saturation current, and this for saturation the condition is VDS greater than VGS minus VTH. Okay, so that means the channel voltage is going to be greater than VGS minus VTH, and therefore the inversion cannot be there on the drain side of the device. Okay, so this is the complete current equation, and yesterday we have seen the plot of this equation. Okay, so now let me come into what happens to the saturation current as you raise the VDS value. I talked about the lambda effect, or the, so there is a parameter which I have put in the SPICE directive. We have used the lambda parameters. Okay, so let me lambda parameter. So what is that lambda parameter? Okay, so what is that lambda parameter? Okay, in the SPICE. So we have used this in order to make the curves basically look slightly different from the ideal curves. So this is basically an ideal curve. So we have not taken into account of the reduction in the length of the channel due to the increased value of VDS, but we need to now take into account of that also. So let me just show. So if we take into account of a slope here, so when I put non-zero value for lambda, what happened is that this current has a slight increase. Okay, so this slope is due to the lambda. Okay, so if lambda is equal to 0, we have flat traces. So this is corresponding to lambda equal to 0. This is like lambda not equal to 0. So you might have seen that I have not explained yesterday when we did the simulation. I just put in some value for lambda like 0.05 or something like that, and then we observed some slope in the curve. So how does that come? So to see that, let us go back again into this diagram. So what I said is that the depletion region extends. So earlier when we derived the expression, what we assumed is that the length of the device is basically from here to here. That means the space between two n plus region, that is what we meant by the length of the device. But then as we biased or as we increased the VDS much larger, then the depletion region extended further, and our effective length is now only this much, because after the pinch off. So especially this effect is more prominent in the saturation region, because after the pinch off the depletion region extends, and then effectively the length of the channel is now L dash. Now what is L dash? L dash is basically L minus delta L. Okay, so delta L is this much. Okay, so that is delta L. So we need to take into account of that, because for saturation current, okay, so for saturation current, we need to consider some second order effect in order to make it more accurate. For saturation current, ID sat, if I rewrite it, mu n Cox by 2, then W by L, then VGS minus VTH the whole square. So here I have taken this as L. I should actually take L dash. So that means ID sat is equal to mu n Cox by 2, then W by L minus L dash into VGS, L minus delta L. The L dash is basically L minus delta L into VGS minus VTH the whole square. So this is going to be our more correct expression. So we are improving the accuracy of the saturation current expression, because in saturation this effect is prominent, but if it is in the other region like VDS less than VTH, the change in L is very negligible. Okay, so we can take it as L itself. The original length, it is more or less correct, because the channel extend from left to right, and there is no much reduction in the length, therefore that expression is okay. But here we need to consider this. Okay, so what I can do is, now I will take this capital L outside and open a bracket and write it as 1 minus delta L by L. So this is mu n Cox by 2 W by L, and then I will have 1 minus delta L by L into VGS minus VTH the whole square. So this is my saturation current. Now I can write, now let us write let delta L by L. Now this is like the fractional change of the length. Okay, now for long channel devices, the delta L by L may be negligible. Okay, so this effect is going to be more prominent when the denominator is smaller. Okay, so that's why we are considering the fractional change. So this is going to be proportional to VDS. Okay, so larger is the VDS. So this is like a model that we are going to fit this change in length. We are going to say that it is proportional to the fractional change in length is going to be. So this is a modeling in order to take into account of what is called as the channel length modulation. Okay, so the channel length is reducing as you increase VDS by large amount, and the rate at which it is going to change, the fractional change, I am approximating by lambda into VDS. So if I substitute that and rewrite the expression, so therefore ID sat is basically equal to mu n Cox by 2 and W by L, and then VGS minus VTH the whole square, and then I will have so this is like 1 minus lambda VDS in the denominator, 1 minus lambda VDS in the denominator raised to minus 1. So this is what now this is an additional term that has come when we try to model the effect of channel length modulation. Okay, so let me write this lambda effect can also correspond to what is called as channel length modulation. So it is one of the effect which is more prominent, especially for small length devices. So lambda parameter is corresponding to the effect of channel length modulation. We are modeling the modeling channel length modulation using a parameter called lambda. Okay, so assuming that this fractional change, which is delta L by L, is smaller, so lambda into VDS is also going to be smaller compared to 1, and if that is the case, then we can use binomial expansion, in which we will only keep the first term. so which is basically 1 plus lambda VDS. So this is approximately equal to mu and Cox by 2 W by L into VGS minus VTH the whole square into 1 plus lambda VDS. Okay, so this is basically I have used a binomial expansion. I hope you are familiar with binomial expansion from mathematics, from class 11 I think it is there. So basically binomial expansion says that 1 plus x raised to some n is basically 1 plus x by 1 factorial sorry, yeah, then sorry, how was it, 1 plus it will be n, sorry, c, yeah, nc 1, right, nc1 into x plus then nc2 into x square plus etc. Okay, so for smaller values of n, x square, x cube, all of that you can neglect. For very very small values of n, so this can be approximated as 1 plus, and nc1 is basically it is going to be nx. Okay, for small values of x. Okay, if you are not remembering, you just go and refresh it about binomial expansion. So I am only keeping the first term, and here it is minus 1. So if you put in 1 plus x is actually minus lambda VDS, so minus lambda VDS into minus 1, so that will give you plus lambda VDS. So that is how that comes. So therefore what we get is basically ID sat is basically the previous current multiplied by 1 plus lambda VDS. Okay, so which is like basically an equation of a straight line. If you look at this is like the x coordinate, and lambda is basically the slope of the line. So larger the slope or larger lambda means larger slope, smaller lambda means smaller slope, or lambda equal to 0 means completely horizontal. So by default in LT Spice it was taking lambda equal to 0, but as you increase your or as you specify it in using the Spice directive, you can have a non-zero lambda. Okay, so that is basically a modified equation which includes what is called as channel length modulation. Okay, so for ID sat. Okay, so another thing I want to say is, if you come back to the characteristics, we are only drawing for one particular VGS here. Now if we had a different VGS, what is going to be the case? So for a different VGS we will have say for example a smaller VGS. So this is for VGS 1 and VGS 2, which is smaller than VGS 1. So then again we will have a linear term, and then there will be a quadratic variation, and then there will be saturation. So the saturation will happen very early. Okay, so like this. So this is for VGS2, where VGS 1 is greater than VGS2. Okay, so you can see that the current basically depends upon what current, the saturation current depends upon VGS values. As VGS increases, the saturation current also increases. So you can draw multiple curves. That's what we did yesterday, but the saturation point will happen earlier and earlier. Okay, so this is VGS3, which is even lesser than VGS2. Okay, so this is a multiple curve that we have seen, that is drawn for and now if we So we have the value of VGS, and then transfer Cara we can draw very easily. So this is our VGS. So if I draw IDS versus VGS, all what you need to do is basically extend this current, the saturation current, and for all this I am just considering 3 saturation current. Okay, this is the saturation level, and similarly here I have another saturation current. So we have VGS, okay, VGS1 somewhere here. So this is VGS1, and then we have VGS2, and then we have VGS3. So 3 means here, 2 here. So if you just draw this, you will get a quadratic relationship, and this is basically our IDS expression, plot of IDS expression. That is this, okay, mu Cox W by L VGS minus VTH all square. So VGS minus VTH, okay, so here the way I have drawn, it looks like our VTH is 0. So that's what we initially drawn, and then by using SPICE directive we have specified the non-zero VTH, and when we have non-zero VTH, what will happen is so everything will be shifted like this. So it will be up to VTH, it will be 0, and then we have like this. Okay, so this is basically our threshold. So when our VGS is so then of course if we have a different or larger if we have a larger VTH, then then the curve will be shifted to the right. Okay, and so if this much current has to flow, VGS should be a relatively larger value. So it means your VGS1 is going to be here, VG2 is going to be here, and VGS3 is going to be here. Okay, so we have plotted that also. Okay, so in the remaining time, I also want to talk about the effect of body bias. Okay, so that is another effect we need to consider. Effect of body bias. So what is body bias? Earlier when we studied the MOS capacitor, the threshold voltage was obtained as what? So VTH. If you remember, if you recall, we had V flat band, then we had a psi S, and then we had what else we had? So flat band voltage would include the difference between work function as well as the voltage that we need to apply to flatten the band because of the oxide layer or oxide region charges. Okay, so both of that included in V flat band. Then we have the surface potential, and then we had basically so surface potential will determine whether at the interface of the semiconductor, whether it is a N region or a P region, whether there is inversion or not. Okay, so and added to that we had the potential across oxide. Okay, so that was psi ox. This was basically the division of VTH. So VTH has these 3 components. So again, if I write so for threshold we said psi S should be 2 phi b. Okay, so only then you are going to have the inversion happening. So when psi S becomes 2 phi b, that means the P substrate near the interface is going to be converted into an n-type material because of the majority carriers, which are going to be electrons. There will be concentration of electrons which is similar to that of the concentration of holes in the bulk. And then we had an equation for psi-ox, if you remember, that was 2 epsilon I q Na, then again so this I am going to put it as psi s. Okay, so psi s, I said for MOS capacitor the psi s was basically equal to 2πb, and that is how we had, and this divided by C-ox. So this was our psi-ox. Okay, so for MOS capacitor, we had psi s is equal to 2πb. Okay, now what will happen if we apply body bias now? But if our if V, what do I mean by VSB, if VSB is not 0, okay, let's say VSB is greater than 0, or to be more general, I can say VSB not equal to 0. So then this equation for threshold voltage is no longer valid. Okay, there will be some changes to it, and if the bulk is going to be applied to a negative potential, okay, if you go back to the schematic diagram, you can see one thing. So look at here. So here the source is applied ground. Source is always ground. Okay, in a MOSFET, source is always at ground. Or source is always the reference with which other potentials we talk about. Okay, so we assume source is the reference, source is the ground. Yeah, and the bulk voltage we can apply positive or negative. Now there is a danger in applying a positive voltage here, because you have a PN junction here. You may end up forward biasing the PN junction, and that will spoil every operation of this device. So you should never forward bias this PN junction, okay, because the current will flow from source to bulk, or from bulk to source. If you apply a positive voltage, and if it is suppose going to be greater than the cut-in voltage of the diode, then you are going to have a huge current, and then everything will get messed up. The MOSFET operation will not happen. So we should never forward bias the PN junction. So, but you are advised to do a reverse bias so that you can reduce this leakage current across the PN junction, because the depletion region is going to become bigger, and as a result you can have a safe operation of the MOSFET. So a negative voltage with respect to source at the bulk is advised, and if you have a negative voltage across a PN junction, as you have learned earlier about the band diagram, so a VSB if VSB is greater than 0, or in particular let us say because the other case we are not interested, we don't want to make a VSB to forward bias the diode. So in other words, VSB greater than 0, okay, because the other case should not be done. Or in particular VSB greater than 0, VSB less than 0 is not advisable. Okay, that will end up forward biasing the diode. Okay, S is N plus. Okay, so N plus voltage become smaller than the P region voltage. It is going to forward bias the diode, which is not good. Okay, so all we can apply is like VSB positive. So what is going to be the effect of that? So that is what so it's like if you draw a PN junction, the band diagram you can draw. So for example, on the P side. So here we have N side. Okay, so if this is the PN junction, without any voltage we can draw a PN junction. So what we need to do is basically, so this is P side. So I have a intrinsic, so intrinsic is this. So this is my EC, EV and EI. And for P side, it is, since it is P type material, I will have this one, that is F, like this. And if there is no voltage applied, it has to be continuous. But then this will come on the N side like this, EI, and then, so this is how we draw the energy band diagram of a PN junction. Okay, so it will go like this. Okay, so here I have assumed there is no voltage applied, so this is N side. So what is this? This is basically EB, energy band diagram for a PN junction with no voltage applied. Okay. Okay, so now if I apply a reverse bias voltage, so you can see that there is a difference, there is a bending in the band. Okay, so and let me denote like this. So this is basically Q into VBI. So VBI is called built in potential. Okay, so VBI is called the built-in potential, and from which we get basically cut-in voltage, etc. for the PN junction. So okay, so for silicon this is going to be larger compared to germanium. Okay, for the difference in the intrinsic carrier concentration, etc. So those are the details. But then now if I apply a reverse bias, what is going to happen is that the Fermi level is going to so we are advised to apply a reverse bias, so that is going to result in so this is the P side, and now the Fermi level cannot be continuous, so wherever we apply okay, so if I apply a reverse bias, then we will basically end up applying a positive potential on the N side. Positive potential means N side will go down in the energy band diagram. So the amount, depending upon the amount of reverse bias, so this is going to be my new Fermi level on the right hand side. So it was here, it was continuous earlier, but it has gone down. P side has gone down, and it's going to be and then you have your EC here, EI here, and then EV here. Okay, so this is on the N side, everything on the N side. And similarly you have ECP, EVP, EIP, and so the difference in the Fermi level. Okay, so now this difference in the Fermi level, okay, so this is EFN and ECN. So this is EFN and then this is EFP. So this is basically Q into applied voltage. Okay, so QV that we applied, or in this case what we are saying is basically we are applying a reverse voltage between what was VSB, VSB or VBS. Okay, so the reverse voltage is basically VBS. So sorry, VSB is okay, this is VSB. Okay, so VSB is positive, that we can do, so which will basically shift the Fermi level like this, and there will be large slope here. Okay, so this is the intrinsic level, so there is more slope. So by applying reverse bias, you are basically creating large barrier. Okay, earlier barrier was there, now it will be creating large barrier. Okay, so this is basically the scenario. Now if we take into account of this, because of this, what is going to happen is that the depletion region will increase. Okay, so our threshold voltage, so VTH dash, okay, the new threshold voltage, V flat band and 2.5B, they will not be affected, but what is going to be affected is the other term, which is the depletion region will increase due to the applied reverse bias, and that is going to be 2 epsilon I Q N A into, so earlier it was psi s was 2.5B. okay, so here I can put 2.5B here. Okay, so I can put 2.5B. So the depletion charge, this is basically depletion charge, this square root of this is depletion charge divided by oxide, that will give you the psi ox. Okay, so this was our psi s, but now because of the reverse bias that I have applied, it is going to become the L. This is something funny. So right now what is going to happen is this psi s, I have to write it as 2.5B plus BSB. So this is going to be the difference divided by Cox. So now this we can write it as okay, so this we can write it as earlier one, so this part has not changed, so this we can write it, if I take a difference between the two, that means delta VTH, so the earlier voltage VTH plus delta VTH, I can write in this manner, where the difference delta VTH is going to be given by 2, this is silicon, okay, this is silicon, Q Na 2.5B plus VSB by Cox. Okay, let me just subtract it from 2 Na 2.5B. Okay, so this thing divided by Cox. So this is what that is going to be equal to. So if I take the common elements outside, so 2 QNA divided by Cox, I can take it outside and then I can write it as 2.5B plus ESP minus square root of 2.5B. Okay, so this is going to be the change in the threshold voltage. Okay, this much is going to be there, and this parameter we can, this is also a spice directive and it is called gamma. Okay, so this is corresponding to body effect parameter corresponding to body effect. Okay, so I will stop here. So we have considered the effect of the application of body bias. Body bias means if you apply a voltage between source and bulk, you cannot apply a forward bias, but you are allowed to apply negative reverse bias voltage, and that will basically it effectively increase the surface potential psi s and increase the depletion region width. Okay, reverse bias always increase the depletion region width, and also it changes the potential. Or in other words, what I am saying is that with respect to the bulk, the gate is or the source is at a larger potential. That is what we mean by VSB positive. So that will raise the silicon substrate potential further. Earlier both were grounded, so it was same potential, but now the potential in the semiconductor side is going to be raised up, and that will increase the depletion region width compared to before. So there will be more depletion charge due to that. Or in other words, you can think is that if bulk is applied a more negative potential, that is going to attract the holes into the bulk terminal, thereby increasing the depletion region inside the device. Okay, so that increased depletion region will increase the charge. So the new amount of charge is given by this surface potential, which is 2 phi b, that was earlier potential, plus your VSB. And this expression here for gamma is not very accurate, but this is a very simple way of deriving it. But actually this gamma is estimated from experiment. Okay, so when you apply the potential, how much is going to be the change in threshold, you find out that from the characteristics, and then take the appropriate value of gamma and substitute it in the model. Okay, so it's more like a empirical parameter rather than you can't really derive the accurate value of gamma. But here I have shown in such a way just to make sure or just to give you an idea what is happening when you apply a negative potential at the bulk compared to the source. It will increase the depletion region, and if it increases the depletion region, it will increase the depletion region charge by some amount. Okay, and as a result, the gate voltage should be more relative to the earlier gate voltage in order to create the inversion layer, because more depletion charge means it has to it has to apply more gate voltage in order to form the inversion layer, and that is because your psi-ox is going to be or the voltage across the oxide layer is going to be larger due to the increase in the depletion charge. Okay, I will stop here.